Good morning, physics students, one and all. It's Mr. Finn coming at you with Finzix, another episode of Finzix from neighborly Northville. Hey guys, this is just an addendum video to the ones you're already seeing today. I have a little bit of things to discuss that are on top of what you've already seen. And that's the idea of magnetic flux. What is magnetic flux? Magnetic flux is actually a combination of the magnetic field strength, B, coupled with or dot product with the area vector through which the magnetic field is exposed. Now, why do we need magnetic flux? Because it leads us into how and how we induce current around these loops of wire. And we're going to need the idea of changing magnetic flux. That means a delta phi. Phi would be the symbol for magnetic flux. So I'm going to go to the board, give you a quick lesson on that, walk you through an example of just how to predict in which way the flux will change or induce a current in a coil. Let's go to the board. Okay guys, I just have a quick example. First of all, the area exposed to the magnetic field. If I have a coil of wire, let's say this coil of wire right here. Here are the two ends of the wire. Here's the coil. That coil will have an area exposed to this magnetic field. Now I have these symbols. You'll see these in your book. If you have a symbol, a circle with a dot in the middle, that means the magnetic field is coming out towards you, the reader. If you have a circle with an X in the middle, that means that the magnetic field is going into the page, plan of the page that you're reading. Obviously, if it's just an arrow this way, or an arrow this way, or an arrow this way, those would all be magnetic fields going those directions. So, these green dots here represent a B that's coming out of the board. Now you may be asking yourself, direction is important. What about the direction of the area? The area can go both ways. It just means that you have to have the area exposed to the magnetic field. So if my magnetic field is coming out of the board, my area obviously is exposed to that field. So my area vector can go out, and that's the way I'll work it. So here's my phi symbol. Phi sub B means flux of magnetic field, magnetic flux. And it is B dot A, or B times A in terms of your multiplication. But dot product means it's got to be in the same direction, parallel. Lenz's law says an induced EMF always gives rise to a current whose magnetic field opposes the original change in flux. Huh? Yes, that's exactly right. So let's take an example. It's best understood with an example. Let's say this coil of wire was sitting in this magnetic field. Well, if it's sitting there, it has a flux, but it doesn't have a changing flux. So there's no current moving in the coil because there's no change in flux. In order for there to be current in the coil, the flux must be changing. Okay, so let's say this area is constant, but the magnetic field is getting stronger. So let's say this green magnetic field coming out of the board is getting bigger. So you've got a vector B facing you that's getting bigger and bigger and bigger and bigger. That means the flux that's facing you is getting bigger. If that flux is facing you is getting bigger, then Lenz's law suggests a current must give rise to a new magnetic field which opposes the change in flux. So if I have a flux going out toward me and getting bigger, that means that Lenz's law suggests there must be a magnetic field going inward that opposes the rise of this flux. And if that magnetic field goes inwards, I use my right-hand rule to determine the direction of that current. So, once again, magnetic field's coming out of the board and getting bigger. In order to oppose that, a new magnetic field must come into play that goes into the board to oppose the rise of the one out of the board. My fingers of my right hand curl in a clockwise direction with this new rise of magnetic field. And guess which way the current moves in this coil of wire? You guessed it, clockwise to support the right-hand rule for the magnetic field going into the board. Wow. The opposite would be true if this magnetic field was decreasing. Let's say you had a magnetic field out of the board, the green dots, but it was decreasing in size. Well, that would mean that a new current would give rise to a magnetic field that opposed the change. Meaning, if I'm getting out of the board but I'm getting smaller, then a magnetic field must come into play that goes out of the board to resist the decrease. And if that happens, I have a new magnetic field coming out of the board that resists the decrease, curl my fingers, and now my fingers go in a counterclockwise direction around the loop. Counterclockwise to support that new magnetic field coming out of the board. Fantastic. Kind of needs some practice, guys. So there's a really good area in your book I'd like you to take a look at. That describes this, and that's the top of page 626. Top of page 626. I'd like you to go over that. Maybe we'll address it in the next episode here. But let me give you one more example. Let's say that this area was moving, but the magnetic field was constant. So this loop is moving to the right. But when it gets past this point, the magnetic field will no longer be there because the magnetic field only exists where the dots are. So let's draw a new coil right there. And you can see that part of that coil has left the field. So if the coil is moving to the right and the magnetic field is not changing, the flux will change when the coil starts to leave the field. Now, how do we know that? That means the area exposed to the field is getting smaller. At this point, if this coil is moving to the right, the area exposed to the field is reducing. What would happen then? Current would give rise to a magnetic field which opposed the decrease in area. So remember, if you have a flux out, the area is getting smaller. That means the flux that is pointed out of the board is getting smaller. A magnetic field must come into existence that opposes that change in flux, meaning out of the field, but out of the board, but decreasing. So a magnetic field will come out of the board along my thumb, curl my right fingers in a clockwise direction because that's the right-hand rule. In this case, current will also go counterclockwise. It's a bit challenging, guys, but there's some excellent examples on the top of page 626. Please review those, and then when I get to the generator and motor one, I'll go through a couple of those with you, and we'll talk about the generator equation in terms of flux. Okay, guys, let's wrap up. Guys, the concept of flux can be a tough one, and changing magnetic flux is a little bit even tougher still. But this is where the meat and the bones of generators and motors are really functioning. We have to know something about flux. It's very, very ethereal. I mean, it's just theoretical out there because you can't reach out and touch flux. But we can see the effects of that all over the place in our motors, generators, and so forth. Make sure you guys get a chance to practice, as this is kind of a tough concept. And I'll be with you to help you out. Make sure you guys are keeping up with the work, and we'll address the flux in generators in a subsequent video. And we'll go through some of those examples if you haven't already done so. Okay, guys, we'll see you soon.